Everyone. So we are going to start chapter 2 in Daniel Steck's Analog Digital Electronics. We're going to cover section 2.1, I think 2.2 here, and then in the next lecture video we'll do 2.3 and then the one after that 2.4. Hopefully that makes sense. And we're going to skip around a little bit in the chapter, but not too much. So this chapter is going to start talking about capacitors and inductors, and that's because we're going to be plugging them into alternating current circuits. Okay. Actually, more accurately, as I mentioned, this is actually just a voltage source that's actually time varying. And this is going to be very useful because the power that we actually get from our outlets are alternating current, where the voltage goes from negative 170 volts to positive 170 volts. And the other thing is actually useful is because you can actually send information using alternating current. So, and we'll talk about how that's going to be used when we get to these filtering circuits. Okay, but let's first review some capacitor basics. And Daniel Steck does not review it too much, but so what I like to do is just add a couple of pictures from my old general physics lecture. So these figures are not what's referenced in this textbook. But when you think about capacitor, you want to think about that. Oh, it's just two parallel plates, and that's the model you actually want to think about. You know, there are technology that makes them a little bit better and stuff like that, but we don't need to think about that. And the idea is that on these two parallel plates, if you apply a voltage across it, what it does is creates an electric field between the two, so that if the ends of this capacitor is connected to into a circuit, what happens is that the charges will build up on one side of the capacitor, and let's say the positive side on this hand, and negative charges will build up on the other side. The cool thing about it is that the amount of charge that is stored on each end of the capacitor, of course, if you add them together, it's actually 0. But when we talk about this charge Q, is actually the amount of charge, let's say, just on the positive end of the capacitor. Okay, that's going to be proportional to basically the voltage change across this capacitor. How much voltage is across this capacitor? Okay, and so we can use this proportionality to basically write this thing called the capacitor law. So now we're back into Steck's equation numbers. So a little bit here. And since charge is proportional to voltage, we can have a constant proportionality between them. And this is for a capacitor, it's going to be called the capacitance. Okay, if you do the little unit analysis on this equation here, you're going to find that the units for capacitance is actually coulombs per volts. But what we're going to do is we're going to make up a new name for it and name it after Michael Faraday, called a farad. Okay, so the unit of a farad, of capacitance of farad, which is, if you go down to the base units, it's actually a coulomb per volt. Okay, so now that we have this basic review of capacitor, what we're going to do is we're actually going to differentiate both sides of this equation. So we have a ddt here, we're going to do a dtt on the other side. Okay, what happens is that on the left hand side you have the time derivative of charge, which is a function of time with respect to time. And we saw that when charges are changing with time, that's actually what produces current. Okay, we're going to have the current symbolized as I. Okay, on the right hand side, the capacitor, right, capacitance is a constant, it doesn't change with time. So that differential actually goes through that and hits the voltage. And then if we're having alternating current, then the voltage will change with time. So therefore, we have the differential with voltage with respect to time. So this is the basic equation for capacitor. And it's very important for us to notice that current only goes through a capacitor when there's a changing voltage with respect to time. So if you have a constant voltage across something, there's no current actually going to flow through that particular capacitor. Okay? And therefore, that's why we need to use alternating current circuit in order for us to flow current through a capacitor. Let's first talk about a few types of capacitor that the book does mention. The first one is a ceramic one. These are going to be very similar to what you picture. And the idea is that you have some electrode on one side, and then you have your wire, right? And this is the wire that sticks out. You can put in your breadboard, and then you have another electrode on the other side, and then that'll stick to the other part of your breadboard. Sandwiched between them is a dielectric. And just to remind you guys what a dielectric is, let's draw that green. A dielectric is a polarizable material, meaning, let's say, right, this side is the side that builds up a bunch of positive charge. The other side is the one that builds up another negative charge. What happens is that the molecules inside the dielectric will align itself so that is the negative molecules, the negative ends of the molecules will be closer to the positive side, where the positive end will be further away. Similarly on the other side, so this will be plus 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 here, and then minus 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 minus, because these things are neutral, right? We have equal number of positive and negative charges in each of these things. Okay, what this does, what the dielectric does, is that it reduces, basically, because this produces a, let's a good color, let's do black. Okay. Right, the capacitor itself produces electric field going this way from the positive to negative, but these dielectrics are producing tiny electric field in the opposite direction, so partially offsetting this electric field. So what happens is that it actually increases the capacitance of your capacitor by inserting these dielectric into the material in between the two parallel plates, so that it reduces electric field, so that the capacitor will not spark when you apply a higher voltage to it. So this actually increases the capacitance of your capacitor. But these are still going to be fairly small, because the capacity of a capacitor is actually proportional to the area of it, and then inversely proportional to the spacing between the two. So you can only make these so big and so much little space between them. So these are going to range from about 1 to 100 picofarad, and a pico is actually 10 to the minus 12 farad. So just so these are very small capacitors, and we're going to use a lot of these in the lab because we tend to deal with small capacitance anyway. Another type of capacitors are the electrolytic. These are, if you imagine, a simple thing about this is that if you imagine two sheets, so let's do a positive sheet, right? This is one of the capacitor plate, and these are going to be big, sheets, right? And then you have a negative sheet, and you stack them on top of each other, right? You have a capacitor, right? But that's not very space efficient. What you can do is then roll this up into like a, roll of toilet paper. You just roll this up, right? And basically you have two overlapping, parallel plates that are tightly bound together with some dielectric between them, just so that we can increase the capacitance, and that way basically allows you to have a very large surface area between the two parallel plates, but still have a small device. And these are going to range from, it's a little tiny battery. Let's have some pictures down here. You can actually see these if you open up some circuits. These little battery looking things, okay, they're not actually a battery, they are capacitors. And one thing about electrolytic capacitor is that they're actually polarized, meaning you're only supposed to have the positive and the negative running one end to the other. Okay, and these are marked by these negative signs here. when we use one of these, I will warn you to make sure to put them in the correct orientation. Okay. The last type of capacitor, what the book mentions, this is the most common one that you'll find in electronics these days. Actually, my phone, my computer screen, cars, light switches, are these tantalum type of capacitor. This is the schematic of it. So let's talk about how this works. So you have one electrode on this side, one electrode on this side. So notice that this electrodes are actually bounded to this tantalum wire, okay, which is a conductor. But this is inserted. So imagine like a pin that goes into a material. You just stick it in there, right? Kind of like a little pin in a cork. And that's inserted into tantalum oxide, which is actually a insulator that's highly polarizable. So that serves as your dielectric. And then outside that, so let's see, this lead here, right, comes up to here, but and gets bonded to a shell outside here. So basically your capacitor, instead of being parallel plate, is kind of like one rod inside a cylinder. Okay, and this gives you a nice medium capacitance type of capacitor, and the capacitance of these things are going to be about 0.1 to about 10 microfarads. So remember, micro is 10 to the minus 6. Just the other ones we didn't mention is nano. You're going to see this in the lab. That's 10 to the minus 9. Okay, and this is what you'll see a lot actually in a lot of consumer electronics. If you like take a hammer to your phone, right, you break it open, you're going to see these little yellow squares, and that's what these tantalum capacitors are. Okay. For connecting multiple capacitors in series and parallel, I'm going to leave this as kind of a homework problem so you can derive it yourself. It's not too bad, just applying, Kirchhoff's law and whether or not, something has the same voltage across it or the same charge across it, and we'll be able to derive these equations. But the answer is here actually. So the capacitors in parallel are actually, they just add normally, where capacitors in series add with this inverse to be consistent with the book. I think this is actually how they denote this previously for resistors. Okay. So they actually have opposite type, equation type compared to resistors. So let's talk about our first circuit involving capacitors, and this is going to be the integrator. Okay, and hopefully that will hint on what the circuit actually does. It does integration. Okay, so in this case, the voltage input here is going to depend on time. This is the alternating current voltage. Okay, and as always, we're interested in figuring out what V out is, as a function of V in, maybe the different components, the resistors and capacitor, and that way we can predict how this circuit actually behave when you drive it with a AC source. Okay, so for now, let's just assume that V out draws no current, right? Because when we're designing circuits, we design a circuit that has a low output impedance and a high input impedance, and therefore this is going to be the output, right? Whatever you're connecting to is going to have a high input impedance, so it's going to draw a little bit of current in order to figure out what V out is, but you want to minimize that as much as possible. So in that case, what happened is that there's really only one current. The current through the resistor, the current through the capacitor is just the same current. So we only have one I. We're just going to call that I. Okay. If we apply Ohm's law, right, it would go from V in to V out. We're going to have a voltage drop, and that voltage drop is going to be the current times the resistor value. And we can use the capacitor equation, which we derived previously, and insert this current into here. Okay. When we insert that current and solve for basically dV dt of V out, you end up with this differential equation that tells you that, well, the time derivative of V out is going to be equal to negative times V out, which is also a function of time, right? Plus V in, which will depend on time also. And both of those factors are going to be divided by the R times C, which is actually known as the RC constant. I'm going to see that that's going to be a special number that has units of inverse time, if I remember right. Okay. So these are actually called ordinary differential equations. And the way we solve this is to kind of go through it step by step. And we're not going to expect you to do this in this class. So I'm just kind of showing you how the book does it, and you know, hopefully that helps you digest what the textbook shows you how to do it. Okay. So first of all, to solve this differential equation, we're going to solve it for the time when V in is equal to 0. So this is a particular solution, but then we're going to generalize that afterward to get the full solution. Okay. Since if we're solving it for the time when V in is equal to 0, this entire term basically disappears. So you just end up with dV out dt equal to negative V out over RC. And the way you solve this is just by separation variable. So you have a bunch of V, you want all the V's on the one side, you want anything that has to do with T on the other side. Okay, so you have dV out dt, and then this also has a V on this side, and then multiply both sides by dt to get the negative 1 over RC dt. Okay, and then you solve this by just integrating both sides. Okay, so something that integrates to 1 over itself, right? So that's actually the natural log of V out. Okay, okay, and then this is not RD, it's RC. 1 over RC is just a constant, and this integral of a constant times dt just gives you t, right? Okay. Well, the solution for this is that, well, you exponentiate both sides, right, to get rid of the natural log. So therefore, this cancel each other. So V out as a function of time is actually going to be, oops, let's not forget the, oh yeah, so there is going to be, you're integrating from 0 to t. Okay, so this is actually, forgot about that, natural log of V out as a function of time minus V out at t equal to 0. Okay, okay, so you exponentiate both sides, get rid of that, and then so you end up with, from up here, V out as a function of time minus V out at time equal to 0, whatever that initial output voltage is, equals to e to the minus t over RC. Okay, solve this for V out. Oh yeah, so one more thing, when you're subtracting two things in a natural log, it's actually the same thing as dividing them. Sorry about that. Okay, so it's actually a ratio between them. That makes more sense. V out is a function of time. Okay, multiply both sides by V out at time equal to 0. We get e to the minus t over RC. Okay, so that's the solution for this short, for this differential equation when V in is actually 0. Okay, so this is only works for this particular solution. So this is not the complete solution yet. Okay, we only solved it for V in at time equal to 0. Okay, but we can see that this solution is going to be some sort of exponential decay. Okay, and to get this complete solution, what we're going to do, we're going to put in this thing called an integrating factor instead of V out. Okay, we're just going to define this new function, this tilde. This doesn't mean the complex number stuff that we're going to talk about in a little bit. It's just a arbitrary function we made up. Okay, and this is going to be equal to v out, whatever that is, with respect to time, right, times some exponential growth function as opposed to a decay function. Okay, in order to satisfy the boundary condition that v out at t equals 0 equals to v0, right, what we need to do is that we're going to have v out as a function of time multiplied by this factor here, right, times e to the minus t over rc, which is exactly what we have previously. Since both factor, right, depends on time, so this one and this one, okay, if we differentiate this v tilde function, we're going to end up with two terms. These two terms are going to be one that's going to be a differential of v out. The other one is going to be a differential of e to the minus t. In the case of the e to the minus, e to the t over rc, in that case, basically what happens is that this 1 over rc factor falls out instead, right? Because if you differentiate e to the alpha x, right? Oops. Let's do x. Differentiate the right variable. You just end up with alpha times e to the alpha x. Okay, so this is looking kind of like our original differential equation that we're trying to solve up here, right, with the v of vn. Okay, so we're going to do, we're going to multiply both sides with e to the positive t to rc, so that we get this equation to look kind of like this one. Okay, so v out t e to the t for rc, right, which basically gets us this term. Oops, r and go to negative v out rc e to the t over rc plus v in times t over rc e to the t over rc. Okay, so basically this term here is equal to this, so we're going to replace that. Okay, right, so that means dv dt is actually going to be this v in, right, as a function of time over rc e to the, keep writing the c wrong. Okay, now if we integrate both sides once again, right, we're going to evaluate it from t equal to 0 to t equals to t, and therefore you have this voltage tilde, which is a function we made up, right. On the right hand side, okay, we're going to have this integral from 0 to 1. We're not even going to be able to evaluate it because we have no idea what Vn is, but, right, we're going to have this factor of Rc that falls up because of that. Okay, now what we're going to do is that we're going to plug this, well, we're going to solve this for V naught, get rid of this, well, solve this for V as a function of t, and then plug it back into equation 2.8 here. Right, so everything here with a positive sign, we're going to plug it into here. Okay, and then we're going to get the complete solution where V out is actually this V naught times e to the minus t time over Rc. Okay, plus 1 over Rc from this factor here. Right, the integral stays the same. Okay, and what happened is that this t to the negative t over Rc gets multiplied into it, and we're going to do a little switcheroo where instead of t, because this t prime in here is actually just the integration variable, so we're going to evaluate, we're going to have this Vn times e to the negative t over Rc times t to the positive t over Rc, t prime over Rc. When you multiply two exponential together, it's the same thing as adding them. So therefore, this will be equal to e to the, we'll put the t prime first, t prime minus t over RC, okay? And that's where this factor comes from down here, okay? And that's the solution for that integrator equation, okay? So the important thing is that, so this circuit, right, if we look at it, there's some constant here, okay, that's going to be, well, it's not constant, it's going to be changing with time, okay? But what we see here is that V out is proportional to basically the integral of V in, okay? And that's going to be a very useful circuit, well, if you want to integrate something. And one of the applications is that, let's say if you have a signal like this, maybe I was going to do an example where it's a bunch of wiggles, right, like this. But then all you care about is, you know, how big is the area under the graph on the signal, right? The integrator basically tells you that, which is sort of neat, okay? So this circuit do integration. Another circuit that we're not going to dive as much into to solve it is the differentiator. Okay, so the main difference between the integrator and differentiator is that you swap the position of the capacitor and the resistor. Okay, when you do the switch, we get the opposite, which is the instead of integration, you get differentiation. Okay, similarly, the way you solve this is that, well, the current, right, is going to be the capacitance of this capacitor, right, instead of the resistor, times the change in voltage across this thing, okay? And since the current is going to be through this part, right, that's from this part, right, the current flowing through this resistor, right, is going to be V out over R using Ohm's law, okay? You can combine these two equations, and then you end up with a differential equation where V out, right, I don't know why they don't put the C here, is going to be proportional to basically the time derivative of V in minus V out. So you have something that is where the output is proportional to the derivative of the input, and then that's what we expect as a differentiator. A cool thing about this circuit is that it allows you to find slopes of functions. Okay, so let's say you have function maybe like this, maybe a little triangular function. What the output is going to look like is going to be, you're going to have positive and negative, positive and negative, because here you have a positive slope, here you have a negative slope, and you can actually do differentiation using circuits. And that's